What's stopping us from visiting our nearest star, Proxima Centauri? From the limits of rocket speed to surviving the cosmic void, here's the science behind humanity's interstellar roadblock. Take the Moon, for example. It's about 384,000 kilometers from Earth. That's a trip astronauts on Apollo 11 completed in just 3 days. Not too bad, right? Now let's go bigger. Mars. Depending on the alignment of the planets, Mars can be 225 million kilometers away. A spacecraft like NASA's Perseverance rover took 7 months to reach it. That's a long trip, but still manageable on a human timescale. But Proxima Centauri? This is where things get wild. At over 40 trillion kilometers, this distance is almost beyond comprehension. If we traveled at the speed of the Apollo 11 spacecraft, about 39,000 kilometers per hour, it would take us nearly 120,000 years to get there. That's longer than the entire history of modern human civilization. That's why astronomers don't measure distances like this in kilometers or miles. They use light years. The distance light travels in a single year. Light moves at an astonishing speed of 300,000 kilometers per second. So in a year, it covers about 9.46 trillion kilometers. When we say Proxima Centauri is 4.24 light-years away, we're saying even light, the fastest thing in the universe, takes over 4 years to make the trip. Now think about this. If it takes us 3 days to reach the Moon, how long would it take to travel trillions of miles? The answer is both humbling and mind-boggling. Humanity would need to redefine what's possible to even dream of such a journey. And that's just the beginning of our challenges. In the next part, we'll explore why our current technology is light-years away from making this epic journey. Don't go anywhere! By the way, if you're as fascinated by the sheer scale of the universe as we are, hit that like button and subscribe. Let us know in the comments, how would you tackle the challenge of traveling to Proxima Centauri? Rocket science may sound like the pinnacle of human ingenuity, but when it comes to interstellar travel, even our most advanced technology feels like crawling. Consider this. The Voyager probes, launched over 45 years ago, are among the fastest human-made objects in space. Voyager 1, for example, travels at a staggering 61,000 kilometers per hour. Impressive, right? But if it were aimed at Proxima Centauri, it would take over 75,000 years to arrive. That's longer than the span of recorded human history. Now imagine starting a road trip, knowing your great-great-grandchildren might finish it for you. Even more modern spacecraft, like NASA's New Horizons, which zipped past Pluto at 58,000 kilometers per hour, don't offer much hope. At that speed, the trip to Proxima Centauri would still take over 78,000 years. And here's the kicker. Those speeds represent the cutting edge of chemical rocket technology, the same basic concept we've been using since the 1940s. Chemical rockets work by burning fuel to produce thrust, but they're constrained by a frustrating rule of physics known as the rocket equation. The tyranny of the rocket equation means that as you try to go faster, you need exponentially more fuel. But here's the catch. Carrying that extra fuel adds weight, which then requires even more fuel to propel. It's a vicious cycle that makes achieving even a fraction of light speed practically impossible with current technology. At best, chemical rockets are perfect for exploring our own solar system, but they're laughably inadequate for journeys to distant stars. So, how do we overcome this limit? Future technologies like light sails, nuclear propulsion, or even antimatter engines might break free from the constraints of chemical propulsion. But right now, we're stuck in first gear on the cosmic highway, painfully aware of just how slow that is. In the next section, we'll take a closer look at these futuristic propulsion methods and ask, could they finally give us the speed we need to explore the stars? Stick around. And before we move on, hit that like button if you're amazed by the sheer scale of this challenge, and tell us in the comments, what's your wildest idea for interstellar travel? Let's talk about the cost of interstellar travel. Not in dollars, but in raw energy. Accelerating a spacecraft to even a modest fraction of the speed of light is like trying to pay a power bill for an entire planet. Here's the staggering truth. To reach just 10% of the speed of light, we'd need an amount of energy equivalent to humanity's entire annual energy consumption. And that's just for one trip. To make this kind of speed achievable, the energy requirements would be orders of magnitude beyond anything we've ever generated. Why is this so extreme? It comes down to the basic physics of acceleration. A spacecraft with even a modest mass requires an enormous amount of energy to overcome inertia and reach such incredible speeds. Traditional chemical rockets are nowhere near efficient enough for this task. Carrying enough fuel on board for such a journey isn't just impractical. It's outright impossible. The more fuel you add, the heavier the spacecraft becomes, creating a self-defeating loop. So, what are the alternatives? Concepts like nuclear propulsion offer one solution. These systems could use nuclear reactions to release far more energy than chemical rockets can. But even nuclear rockets, while efficient, wouldn't come close to the energy levels required for interstellar travel. Then there's antimatter propulsion, the holy grail of energy sources. Antimatter releases almost 100% of its mass as energy when it annihilates with regular matter, making it astonishingly powerful. Theoretically, just a few grams of antimatter could propel a spacecraft at significant fractions of light speed. But here's the catch. Producing, storing, and controlling antimatter is still a monumental technical challenge. Right now, humanity can only produce antimatter in microscopic amounts, at astronomical costs. Even cutting-edge ideas like light sails powered by massive ground-based lasers face similar energy hurdles. Generating and focusing that much power would require an infrastructure so vast it sounds more like science fiction than science fact. The energy demands of interstellar travel push the boundaries of what's even conceivable. We're talking about creating power systems capable of outputting energies far beyond anything humanity has ever managed. So, is it even possible? That's a question we'll explore as we dive deeper into the realm of futuristic propulsion systems and innovative solutions. But before we get to that, let's pause for a moment. If this level of ambition amazes you, or even feels a little overwhelming, smash that like button. And tell us in the comments, if energy weren't an issue, what kind of spacecraft would you design to explore the stars? If reaching the stars weren't challenging enough, there's another wrinkle in our cosmic plans. Time itself doesn't behave the way we expect when you're traveling near the speed of light. Thanks to Einstein's theory of special relativity, the faster you move, the more time slows down for you compared to someone standing still. So, could traveling to Proxima Centauri actually turn us into time travelers? And what happens to the people we leave behind? Here's how it works. Imagine a spacecraft capable of reaching 10% of the speed of light, a velocity far beyond anything humanity has achieved so far. At this speed, time dilation starts to become noticeable. But as you push closer to 99% of the speed of light, the effects become extreme. For travelers aboard the spacecraft, time would pass far more slowly than it does for those back on Earth. If your journey to Proxima Centauri took 8 years round trip at near-light speed, people on Earth might experience decades, or even centuries, of time passing while you're away. For the crew, it would feel like only a few years had passed, but they'd return to a planet that had changed in unimaginable ways. This phenomenon, while fascinating, complicates interstellar missions in profound ways. Would astronauts be willing to leave behind everything they know, knowing that by the time they return, everyone they loved might be long gone? And let's not forget the practical challenges. Relativity impacts communication too. If a message sent from Earth takes over 4 years to reach a spacecraft near Proxima Centauri, and the reply takes just as long, meaningful real-time interaction is impossible. Add time dilation into the mix, and coordinating a mission becomes a logistical nightmare. But could time dilation actually work in our favor? From the perspective of the travelers, the journey would feel much shorter than it actually is. For instance, a ship traveling at 90% of the speed of light could make it to Proxima Centauri in what feels like just a few months to the crew, even though years would pass for everyone else. This makes interstellar missions more plausible, at least for the people on the ship, but it still doesn't solve the problem of reconnecting with Earth's timeline. Relativity doesn't just bend time, it warps our understanding of what's possible. In a way, interstellar travelers would become explorers, not just of space, but of time itself, stepping into a future far removed from the one they left behind. This might be the ultimate price of interstellar travel. Not just the energy, the technology, or the distance, but the emotional cost of leaving our present behind. In the next section, we'll dive into what humanity might do to overcome these obstacles and whether we'll ever truly be ready to embrace the strange realities of interstellar exploration. If this concept of time travel blows your mind, let us know in the comments below. And don't forget to like and subscribe if you're ready to journey further into the cosmos. Space may seem like the final frontier, but it's also a profoundly hostile environment. To travel to Proxima Centauri, humans would have to endure a journey lasting decades, if not centuries, trapped in a spacecraft, hurtling through a deadly vacuum. Could we survive such a mission? The answer might make you reconsider your favorite sci-fi fantasies. First, there's the invisible killer, cosmic radiation. Outside the protective bubble of Earth's atmosphere and magnetic field, astronauts are bombarded by high-energy particles from the Sun and distant stars. Over years of exposure, this radiation can damage DNA, increase cancer risk, and even impair brain function. Shielding against this radiation isn't simple. Thick walls add weight, which increases fuel requirements. Innovative ideas like using water or even human waste as shielding have been proposed, but there's no perfect solution yet. Then there's the question of life support. For a journey to Proxima Centauri, a spacecraft would need to sustain its crew for decades, possibly even centuries. That means providing air, water, and food in a completely closed-loop system. Recycling these essentials is already challenging on the International Space Station, where missions last only a few months. Scaling this up for an interstellar journey would require breakthroughs in biotechnology. For example, growing food in space, something we're just starting to experiment with, would need to become a reliable and efficient process. And what about waste? Everything would need to be recycled and reused with almost no loss, creating a system that feels more like an ecosystem than a spaceship. But even if we solve the technical problems, there's one challenge we can't engineer our way out of: the psychological toll of isolation and confinement. Imagine spending decades in a cramped spacecraft, cut off from the rest of humanity, with only a handful of crewmates for company. Loneliness, cabin fever, and interpersonal conflicts could become serious issues over time. Studies on long-term isolation, like those conducted in Antarctic research stations or Mars simulation habitats, show that mental health can deteriorate quickly without proper support. And unlike on Earth, there's no escape hatch when you're halfway to another star. To survive such a journey, we'd need not only technological innovations but also a deep understanding of human resilience. Could we train astronauts to handle the immense psychological pressure? Would we need to send people in cryosleep or even create multi-generational missions where the crew's descendants complete the journey? These are questions we don't yet have answers to. In the end, the greatest challenge of interstellar travel might not be the vast distances, the energy requirements, or the engineering feats. It might be the human element. Are we ready to face the void? In the next section, we'll explore how futuristic concepts like artificial intelligence and robotics could help us bridge the gap to Proxima Centauri. If this glimpse into the harsh realities of space travel has you rethinking interstellar exploration, let us know in the comments. And don't forget to like and subscribe, because even if humans can't survive the journey yet, our curiosity always will. Reaching Proxima Centauri isn't just a question of traveling fast. It's about traveling with precision. Imagine firing a bullet at a target so far away that even the tiniest miscalculation could send it veering off course forever. That's the challenge of navigating to a star system light years away. So, how do we avoid missing the mark and ending up lost in the endless void of space? First, we have to consider that Proxima Centauri isn't standing still. Like every other object in the galaxy, it's hurtling through space, orbiting the Milky Way at incredible speeds. By the time a spacecraft launched today reached its destination decades or centuries later, Proxima Centauri would be in a completely different position. To succeed, mission planners would need to calculate its future location with extreme accuracy, factoring in not just the star's movement, but also gravitational influences from other celestial bodies. This isn't an easy task. Even the slightest error in these calculations could result in missing the star entirely, sending the spacecraft on a one-way trip into interstellar emptiness. And missing doesn't just mean failure, it means catastrophe. With no way to turn around or adjust course significantly once the spacecraft is traveling at relativistic speeds, a mistaken navigation could leave it drifting aimlessly through space forever. To prevent this, we'd need advanced onboard systems capable of continuously recalculating the spacecraft's trajectory. These systems would have to account for unforeseen factors like gravitational anomalies or the movement of previously undetected objects. Then there's the problem of avoiding obstacles en route. Space might seem empty, but even a tiny particle at relativistic speeds can wreak havoc. A grain of dust or a rogue asteroid could destroy a spacecraft traveling at a significant fraction of the speed of light. Detecting and navigating around these obstacles requires unprecedented levels of precision. Advanced sensors and shielding would be essential, but even with these, the risks are immense. Some scientists suggest using a massive laser array to clear debris ahead of the spacecraft, but this idea remains purely theoretical for now. So how do we stay on target across such vast distances? The answer may lie in autonomous navigation systems powered by artificial intelligence. These systems could use onboard telescopes and sensors to make real-time adjustments, constantly refining the spacecraft's course as it travels. They'd essentially act as the ship's eyes and brain, ensuring it stays locked onto Proxima Centauri even as the galaxy shifts around it. Ultimately, navigating to another star is like trying to hit a moving target while you're also moving, and doing so without a safety net. Even a slight miscalculation could doom the mission to failure. In the next section, we'll explore whether artificial intelligence could become the key to solving these problems and ensuring our spacecraft survives the journey. If this glimpse into the complexities of interstellar navigation has your mind racing, hit that like button and share your thoughts in the comments. And don't forget to subscribe. We've still got more to uncover as we chart humanity's path to the stars. Despite the overwhelming challenges of interstellar travel, humanity isn't giving up. From experimental propulsion systems to groundbreaking initiatives, there's a growing sense of hope that the impossible might one day become achievable. Could humanity's next great leap be hiding in technology we haven't even discovered yet? One of the most exciting projects currently in development is Breakthrough Starshot, a bold initiative to send tiny, lightweight spacecraft to Proxima Centauri. These probes, no larger than a postage stamp, would be equipped with cameras, sensors, and communication devices. The real genius lies in how they'd travel, using light sails powered by an array of ground-based lasers. These lasers would fire powerful beams of light, pushing the sails to speeds of up to 20% of the speed of light. If successful, these microprobes could reach Proxima Centauri in just over 20 years. It's an ambitious plan, but challenges like building a laser system powerful enough and ensuring the probes survive the harsh conditions of interstellar space still need to be overcome. Another promising avenue is fusion propulsion. Unlike chemical rockets, which are limited by their inefficient fuel-to-thrust ratio, fusion engines would harness the immense energy released by fusing atomic nuclei, similar to how the sun produces energy. A fusion-powered spacecraft could achieve speeds far greater than anything possible today, drastically reducing travel times. But here's the catch. While we're making progress on Earth with experimental fusion reactors, building a compact, reliable system for a spacecraft remains a monumental challenge. Then, there's the ultimate sci-fi dream: antimatter propulsion. When matter and antimatter collide, they annihilate each other, releasing energy with unparalleled efficiency. A gram of antimatter could theoretically produce as much energy as the fuel required to launch dozens of rockets. But producing antimatter in usable quantities is currently prohibitively expensive, billions of dollars for just a few micrograms. Even if we solve that issue, storing and safely handling antimatter would require revolutionary new technologies. And what about breaking the rules altogether? Concepts like warp drives, inspired by Einstein's theory of general relativity, suggest it might one day be possible to bend space-time itself, creating a bubble that allows a spacecraft to travel faster than light without violating the laws of physics. While still highly theoretical, scientists like Miguel Alcubierre have proposed mathematical models for how this might work. It's a tantalizing idea, but one that's likely far beyond our current understanding of physics. None of these breakthroughs would be possible without artificial intelligence and automation. AI could play a critical role in everything from navigating interstellar distances to managing life support systems on long-duration missions. Robots and automated systems might even pave the way for human exploration by building infrastructure on alien worlds before we arrive. Humanity's dreams of reaching the stars may seem out of reach today, but history has shown us that what seems impossible often becomes reality with time, innovation, and determination. After all, it wasn't long ago that the idea of landing on the moon seemed just as far-fetched. So, what will it take to make these dreams a reality? Maybe a new energy source, a breakthrough in physics, or an entirely new way of thinking about space travel. The one thing we know for sure is that the desire to explore is written into the very fabric of who we are. If this glimpse into the future of interstellar travel inspires you, hit that like button and subscribe for more. And let us know in the comments, which breakthrough do you think will get us to the stars? So, why are we so eager to journey to Proxima Centauri? What's waiting for us at the end of this cosmic marathon? The answer lies with a fascinating world orbiting this nearby star. Proxima b, an exoplanet that has captured the imagination of scientists and dreamers alike. But is it a new Earth or a barren wasteland? What will we find when we finally arrive? Proxima b sits in the habitable zone of its parent star, a sweet spot where temperatures could allow liquid water to exist. At just 1.2 times the mass of Earth, it's tantalizingly similar to our home planet. If Proxima b has an atmosphere, it might even be capable of supporting life as we know it. But there's a catch. Proxima Centauri is a red dwarf star, far smaller and cooler than our Sun. Red dwarfs are notorious for their violent solar flares, which can strip away a planet's atmosphere and bathe the surface in deadly radiation. If Proxima b doesn't have a strong magnetic field or a thick atmosphere to shield it, life as we know it might be impossible. So, could Proxima b host life? Right now, we just don't know. Telescopes like the James Webb Space Telescope and future observatories may help us analyze Proxima b's atmosphere, if it has one. By studying how the planet's atmosphere interacts with the light from its star, we might be able to detect signs of water, oxygen, or even more complex molecules that hint at biological processes. But even with these cutting-edge tools, remotely confirming habitability, or life, will be incredibly difficult. And yet, the potential discoveries make the journey worth it. Imagine being the first to detect alien life, or even just the conditions for it, on a world outside our solar system. Even if Proxima b turns out to be barren, it will teach us invaluable lessons about planetary systems, atmospheres, and the evolution of planets around red dwarf stars. These insights could guide our search for other potentially habitable worlds. But beyond the scientific value, there's a deeper reason we're so captivated by Proxima b: the dream of finding a second home. As humanity faces mounting challenges on Earth, from climate change to overpopulation, the idea of a new world, one that could ensure the survival of our species, has never felt more urgent. So, is the journey worth it? For the chance to answer one of humanity's most profound questions, are we alone in the universe? The answer is a resounding yes. Whether we find life, a new Earth, or simply an empty rock, the search itself is an adventure worth pursuing.